is a big specialist. I think that it's not necessary for me to talk a lot about him, but just to mention that Peter Schenzel together with Ngô Việt Trung and Nguyễn Từ Cương introduced the notion of generalized cohomology module, and that became a very popular topic for already 50 years. And he's of course from the first work, he worked on local cohomology, Koszul homology, completion, and so on. And today he, I think he gave a part of his research on this topic. So please, Peter Schenzel.
Thank you, Hoa, for the introduction and for the nice words about my friends Hoa, Chung, and Kwong. Okay. Secondly, let me thank you, Yugal and Kriti, for helping me with the technical details. Okay, so now let me start about my talk. I want to say something news about Koszul and Czech complexes. For the first, this seems to be not possible to find something new, but I was surprised about that. But before I will go on, I want to say something about the fathers and grandfathers of the subject. First, let me mention Eduard Czech. He was born in 1893 in Bohemia. In 1912, he became a student at Charles University in Praha, and he stopped his studies in between and became 3 years soldier in the World War first, and after that he became a teacher, and he continued with his work mostly about differential geometry, where he got his PhD in 1920. Then he was visiting Lefschetz in Princeton, and in 1932 he introduced what nowadays is called Czech homology theory. And by the work of Grothendieck, this is nowadays related to what we call Czech complex in commutative algebra. In 1956, he became director of the Mathematical Institute of the Czech Academy of Sciences, and he died 1960 in Prague. He was the most famous Czech mathematician of the 20th century. Okay, the second name I want to mention is Jean-Louis Koszul, because it is as Czech is included in the title of my talk. Koszul was born in 1921 in Strasbourg, and he was the son of a professor and became itself a professor 1956 at the University of Strasbourg, and in 1963 he moved to Grenoble. Since 1940, he became one of the members of the second generation of the Bourbaki group, including Dijmier, Godemont, Eilenberg, Samuel Serre, and Laurent Schwartz. He worked about homology and cohomology of Lie algebras, and in this context, he introduced a construction which is nowadays called Koszul complex. Some particular cases of Koszul complexes were known, of course, before. And in 1978, he became president of the French Mathematical Society, and later he became member of Academy of Sciences of the French Academy. In 2018, he died. Okay, the third name I want to mention is Francis Sowerby Macaulay. Macaulay was born in 1862 in Whitney, and his father was minister in the Methodistic Church, and in 1879 he became a member of the John's College in Cambridge, and later on he went back to the Kingswood School in Bath and became teacher in 1985 at the St. Paul's School in London. He was 25 years a teacher at the school, and some of his pupils were Watson and Littlewood. And later on, he moved from London to Cambridge and was since 1928 Fellow of the Royal Society. Besides of David Hilbert, one could say that Macaulay was one of our grandfathers and most inspiring for commutative algebra, including his work about resolution and so on. I will come back to this later. Okay. So what is the program of my talk? In the first part of the talk, I want to present some elementary facts about Koszul and Czech complexes, just with respect to a single element. And the intention is to construct a free resolution of the Czech complex for system elements in a commutative ring. This has some interesting consequences, which I will explain later on. Okay. This construction gives the quasi-isomorphism between Czech complex and a certain Koszul complex. You might know that the Czech complex itself is a direct limit of certain Koszul complexes. We will respect the Czech complex with a quasi-isomorphism to a certain new kind of Koszul complex, which I will explain later on. Okay, we will find this free resolution of the Czech complex in order to find relations to left-derived functors of the completion as a certain Koszul homology. I will not say too many things, only a few words about derived categories and derived functors. My idea is to explain things from the basic with an instruction for reading some recent work done by Anne-Marie Simon and myself. And finally, I will give an application of these constructions to a construction in number theory called prisms, given by Budd and Scholze in a recent paper. Oh, sorry, where is it? Oh, sorry. Oh, sorry, I will not. I am not very familiar with all these things. Okay, here was a paper by Budd and Scholze. Okay, so now let me see how to find back. Okay, let me start again. Sorry about that. Okay, so what are the requirements for my talk? I want to have a little basic knowledge about commutative algebra given, for instance, in the book by Matsumura or even in the book by Balwant Singh. I met Balwant Singh almost 40 years ago when he gives some talks about resolution of singularities in at the University of Halle. Some basic knowledge about homological algebra, for instance, in the book by Rodman, or even by the book by Vermani. It is worth to say that up to now there's no real elementary introduction to homological algebra for people in commutative ring theory. And I think the book of Vermani, in some sense, fills this gap. Okay, let me continue with a final remark. If I have a morphism of two complexes, it is called quasi-isomorphism. If it induces an isomorphism for the cohomology for all degrees, and I will write it symbolically in this way. And I write X simultaneously Y if there is a finite sequence of quasi-isomorphisms of this type. That is the only technical notion about quasi-isomorphism and derived stuff I will need. Okay, let me have a short look at the plan of the talk. I will give some preliminaries. I will construct some kind of sequences interested in the subject, and I will give relations to completions and local cohomology. I have some applications, and in the second part of my talk next week, I will say something about duality and pro-regular sequences and some local conditions related to the work of Bad and Scholze. Okay, let me start. Always I will denote by R a commutative ring. M is an R module. The ring in general is not to be assumed to be Noetherian, and the module is not necessarily finite generated. I should denote an ideal X an element. With the underline X, I denote a system of elements, and X and Y should denote two complexes. We have always for an element and a module the multiplication map that maps M to the element xm in the module. And the kernel of this multiplication map is the annihilator of x in M, and the co-kernel is a factor module. This is some trivial thing, and I call mu x injective if and only if x is M regular. And sometimes this is called quasi-M regular, but I will follow here the simplified notation. And mu x is surjective if and only if M is x divisible. That means any element can be written as a multiple of x. Okay. I want to make some generalizations to complexes. For this reason, I am looking for a morphism between two complexes, and I am looking for the mapping cone. With a -1 here in the subscription, I will denote the shift by -1 for a complex. In the case of a co-complex, I will write the upper -1. The mapping cone provides a short exact sequence of this type. This is one of the main constructions, and I can extend the multiplication map from a module to the case of a complex by doing it degree-wise. And I call the Koszul complex of x with respect to this complex as a mapping cone with this multiplication map. And I call HIX the homology of this Koszul complex. Okay, you might see the construction. We have here a commutative diagram with a short exact sequence of complexes where M is a complex considered in degree 0. Here I have the Koszul complex, and here the complex M and shifted in degree 1. One can generalize this to the situation of a complex, and we have a short exact sequence of this kind of Koszul complex with the complexes X and its shift. It induces a long exact homology sequence of this type, where it is easily seen that the multiplication between these two homology modules is given by plus or minus X. I was not willing to write the precise sign here. And I can split up this long exact sequence in short exact sequences of the following type. The co-kernel of this map is just H0 of the i's homology, and the kernel of this map is just I of x I minus 1 homology. This holds for all I. So I have a good control of the homology of this Koszul complex in terms of the homology of X. Okay, it is easily seen that this Koszul complex is a tensor product of the Koszul complex of R with the complex of X itself. And often I write for the Koszul complex of the element in the ring, I use this abbreviation. Okay, for a system of elements, I make an inductive definition. I define the Koszul complex with respect to this system of elements and the complex X recursively as I have done it before. Okay, and it comes out that this is a tensor product of this Koszul complexes with respect to a single element and the complex X itself. Okay, there's a dual construction, the so-called co-Koszul complex. For this, I need the construction of the fiber cone. If F is a morphism of co-complexes, I define the fiber of F just as a cone shifted in degree 1. So I have a short exact sequence of complexes here. And I define the Koszul co-complex as a fiber of the multiplication map with respect to X on the complex X. Okay, and the same, I do it for a sequence of elements in a similar way as above. Okay, so maybe this is not so important because up to a shift, the Koszul complex and the co-complex are isomorphic. That means also that the homology and the cohomology are isomorphic up to a mirroring against K. Okay, but why I am interested in Koszul complexes and co-Koszul complexes, this has to do with the following. We have here a map between two Koszul complexes. One is a multiplication with respect to xm, and the second one is with respect to the multiplication of x to the n. And the vertical arrow is a multiplication with respect to x to m minus n. I have, on the other side, I have for the co-Koszul complexes, I have a dual situation from multiplication here, and here again, the multiplication with the power x to m minus 1. So we have here an inverse system of this simple Koszul complexes, and here I have a direct system of this kind of Koszul complexes. Okay, let us first look at the direct system. The direct limits leads the complex Cx, and here I have R, and here I have the limit of the following in a direct system R, and the multiplication from one component to a second is given by X. Okay, so what is this limit? We have the classical definition of the direct limit. I have to take the direct sum of all components in the system with a certain transition map, and as I co-kernel, I get the limit. Okay, so let me introduce for counting the integers a variable u, and the same here. Then the transition map is given by the multiplication with 1 minus xu, and I have here the co-kernel, and this gives the isomorphism to the limit. And clearly, the last module here, this is just the localization with respect to the single element x. Okay, this leads to a free resolution of the localization with respect to x. Namely, I have this complex Px given by Ru with a multiplication map and so on. This is a free resolution of R localized at x. What comes out here is the fact, clearly, the flat dimension of R localized at x is 0 because it is a flat module. And we see here that the projective dimension of the localization is at most 1. You might discuss when it is 0 or 1. Okay, so the Czech complex is the following complex. I take R and the map to the localization, and I tensor it with M, and I get this natural map where, for a module where M is mapped to M over 1. And I have, for the cohomology of this complex, in the case of a module, I have the union of all annihilators of the powers of x to n in M, and I use this definition with a with this kind of brackets. Okay, and for H1, I have just it's isomorphic to the localization with respect to x and the image of this natural map, or as we have seen above, I can write it in this way as this limit where I have here the factors and the image in the direct system is given by the multiplication with x. Okay, a few constructions and definitions. Of course, this Czech complex is just the fiber of this natural map here. And this is extended to an R complex in the natural way. I have the map for complexes with respect to the localization, and I take the Czech complex in this way as a fiber over this natural map. And this is, in fact, the Czech complex for a single element over R with tensored with X. And I do it the same for a system of elements in the inductive way, and I have here this tensor product. And I define Hi Czech with respect to x of x as a homology, as a cohomology of the Czech complex. Okay. So the basic diagram. Now, up to now, I made some repetitions of known facts, but now I want to describe you, at least for me, it was some new observation. I have a morphism of complexes. Namely, I take this resolution as given above, and I have a map in degree 0 from R to this one, and I complete it to the commutative diagram. So I have here the identity, and here is just given the resolution of this localization. Okay, and this induces a quasi-isomorphism of fiber cones, namely the fiber cone of g of x with, and the fiber cone with of iota x, which is the Czech complex. And I call this fiber cone of gx Czech L with respect to x. And it gives, in fact, a free resolution. This complex consists of 3 R modules. You can look at the previous definitions, and if you put it together, you might see this notation, where this is just a counting sitting in degree in counting -1, and I have here the polynomial ring. That means the direct sum over the integers of R and so on. And this map is given in the following way. It is easy to see from the previous construction. And for a sequence of elements, I do inductively define this complex Czech L inductively by the tensor product, and this is a complex of 3 R modules. And what comes out? I have a resolution of the Czech complex because this induces a quasi-isomorphism between this new construction with a Czech complex, and for an arbitrary complex, I define it in this way. Okay, so that means the Czech cohomology, as I defined before, is given as a cohomology of a pre-complex tensored with X. Okay. Let me discuss a slight variation of this complex. I make a shift in the following way. I define a new complex consisting of two stages in the following way. I define a polynomial in U mapping in this way. Okay? And I have a commutative diagram in the following way. I have here what I have done before, and recall that this is just a shift of the previous one, where I have it. Here you can see this complex, and the new one with Lx is just a shift, and I have the following commutative diagram with psi x given here above, and I have here the Czech complex, and the vertical maps are given in this way. I take a polynomial in U and map it to the first constant, and here I replace a polynomial this way by substituting U to 1 over x. Okay. And what is the interest point here? This defines a quasi-isomorphism. That means an isomorphism in cohomology. That means we have another free resolution of the Czech complex. And I want to play a little bit around with the two complexes here. This is the previous one, and this is the one shifted. And here I have a complex consisting of the identity that maps R U minus 1 to R. And this provides a short exact sequence of complexes. And what comes out? It is easy to define the vertical maps and to prove commutativity and exactness. And what I have here, because this is an exact complex, it comes out that I have a direct decomposition of this Czech L as an isomorphism to L plus this exact complex E. Okay, so that means L1x gives a free resolution of the Czech complex. This is another one, and I continue with a definition for a sequence in the inductive way and tensoring with a complex, and I have in altogether quasi-isomorphisms of the following way. Okay, you might ask why it is of some interest to make this shift. This will become clear a little bit later. Namely, I want to explain what is the advantage of this complex, and this will come in a few minutes later. I have another kind of simple Koszul complexes. To this end, I define for a module M the polynomial module and the formal power series module. Okay, one can define this formal power series module as a set of homomorphisms of U into M. If X is a complex, I can do this construction degree-wise, and I will get a new complex of formal power series. Okay, let me come back to a very simple Koszul complex. For the module in one variable, and I take the element X minus U, because the cohomology of this module is annihilated by this sequence. It comes out, it is in fact the cohomology are R modules. And it is easy to see, in this case, the zeros homology is M here. because there's just a substitution for u by x, and you can mod out it, and you will have m. And the first homology is 0, because this acts as a regular element here. Okay, let me ask you a problem. What is the same situation if I take the formal power series module? What is a homology here? And is it 0, or comes out, the first is 0, or the zeros is m? I was a little bit surprised. It is not so easy to handle this complex. To this end, I call m of bounded x torsion if this kind of annihilator stabilizes for large n. That means this quotient, which is a union of all of them, is equal to the annihilator for xk for some large k. Okay, recall that we are working not in necessarily in Noetherian rings and finite degenerated modules, so this makes sense. And what comes out here, the zeros homology here is just the module, formal power series module. Module is a submodule generated by x minus u. And I have a map to the completion of m with respect to xr. And the kernel of this natural map is the first homology here. And it comes out, if m is of bounded x torsion, we have that the zeros homology, no, sorry, this is a misprint here. This should be the first homology, and this is zero homology. Sorry about that. Okay, let me sketch a proof. If I take an element of the formal power series module, I can write it in this way. And in the Koszul complex, it is mapped to the multiplication, which looks like this. Okay, and if I take the class here, I can map it to the first tail, to the starting tail of this formal power series, modulo xi for all I. And it is easily seen that this is in fact an element of the completion with respect to xr of m. Okay, and I can find out that this homomorphism module is the inverse limit of m with a multiplication of x, and this kind of homomorphism can be written as the infinite sequence with this property. And then it's easy to show that the first homology is 0, and it makes some more effort in order to prove that this is really an isomorphism. Okay, now I have the formal power series module can be written as the inverse limit of the polynomial module modulo u to the n, where this becomes an inverse system with the natural epimorphisms. Okay, and for this Koszul complex, it is easy to see that this is isomorphic to the inverse limit of this Koszul complexes, where I have this element x minus u with respect to this factor module. Okay, and what is this complex here? I'm looking for it in the following way. I define a map to the ordinary Koszul complex of m with respect to the nth power of x. Where the vertical maps, I map the truncated sequence here. In fact, we are working with R modules, so I can take this element here, and I map it to the last entry with a sitting in degree n minus 1. Okay, and it is a nice exercise to prove that this is a quasi-isomorphism, and that means I have an interpretation of this homology here, and this gives, or before I will give another application, I will say something about an alternative proof of this fact. I enlarge the causal complex a little bit. I take the causal complex with respect to two elements, x minus u and u to the n, with respect to mu, the polynomial module. And this is isomorphic to x to the n, to the causal complex generated by x to the n and x minus u, because both are equal. And this complex here is isomorphic to this one. You can write this as a tensor product of the causal complex of this with respect to mu and the causal complex with respect to un with respect to mu, and then it induces a quasi-isomorphism. And on the other side, if I take the second one, I have this quasi-isomorphism. I mod out x minus u, this becomes m in homology, and it respects quasi-isomorphism, and this is this one. So I get, because this is quasi-isomorphic, both of them are quasi-isomorphic. Okay, by some short exact sequence for inverse limits, I have this explanation for the homology, for the causal homology of this complex. What is the fazit? So causal homology of this is, of course, 0 for I not equal to 0 and 1. And I have this short exact sequence for the zeros homology that gives me another interpretation of the map I discussed before. And I have here again, so first homology is given as a direct limit here. You can read it up from this cohomology sequence. By the way, this short exact sequence comes from the fact that in the definition here, the inverse system is onto, that it satisfies the Mittag-Leffler condition. So I have this sequence here as I explained it here in this way. Okay. So, but now I want to say we have we have an interpretation of this causal complex with respect to the formal power series complexes, and I will come back to the complex Lx given in this way with this map, and I will have a diagram including the dual and the causal complex of this one, namely in the following way. I have here, I take an isomorphism here, because this is just a shift in degree, and here I can identify it, and I have a map rho x, which maps the formal power series in this way. Okay. What comes out here? Derived functor with a Czech complex in respect to m has a representative in this way. I can replace the Czech complex by a complex of 3 modules, and this is in fact a causal complex. So that means because of my knowledge that I have a free resolution of the Czech complex, I can give this complex in interpretation as a causal complex with respect to formal power series module. Okay, now what is a natural question to ask? Is there a representation of this complex Lx tensored with m, which is isomorphic, quasi-isomorphic to the Czech complex, as a certain co-causal complex? And this will be it's a problem which I will discuss a little bit later. Namely, let us start with a Czech complex of the polynomial module with respect to a single element. And by definition, this is a direct limit of the Koszul co-complex of this way. Okay, and we know because U is a regular element on this polynomial module, this is quasi-isomorphic to the first homology module, and this is in fact the direct limit of this quotient with a multiplication by U sitting in degree 1. This was explained in more detail before. Okay, so I have that this limit is isomorphic to the Czech homology of the polynomial module with respect to a single element, and this is just the localization with respect to U modulo mu, and this is isomorphic to what we call m to u minus 1, where the U module structure of this is given in the following way. I define ui times mu to the power minus j 0 if I is bigger than j, and otherwise I define it as m times u to I minus j if I is smaller than j, smaller than or equal to j. This is Macaulay's inverse system in one variable over m. I will give the reference a little bit later. And I want to construct a quasi-isomorphism between this Koszul complex and the Czech complex. So I take this co-Koszul complex with a multiplication by xu, and I have here the polynomial, the inverse polynomials, and I take some maps to the Czech complex in the following way. I define f to some polynomial in u minus 1 to the constant, and f1 is given by, I make a substitution of u by x and divide out x. And this is a good exercise for learning something about quasi-isomorphism, to prove that this Koszul complex here is quasi-isomorphic to the Czech complex. So I have a free resolution of the Czech complex as a certain Koszul complex, because this is a complex of 3 R modules. Okay. I will continue with some sequences. Of course, Koszul complexes are not defined only for a single element. So I will take the underline of U, a set of variables in the same amount as I have elements in the sequence X. And I will take the polynomial ring in this new variables u1 up to uk, and I take the inverse polynomials in the same variables with the module structure extended in the natural way as I have done it before. And I will define a sequence x minus u as a x1 minus u1 and so on in this polynomial ring. Okay, and if X is an R complex, I extend all these constructions to the complex. I will take the polynomial module in K variables, the inverse polynomials in K variables, and so on. I have this tensor product here and this dual construction. Okay, and I make iterative constructions of this in the way I take the Koszul complex with the sequence of elements, and this is almost immediately to see that this is isomorphic, quasi-isomorphic. And the homology is called the Czech homology, the Czech homology with respect to X. Okay. And what I know, I have isomorphisms, quasi-isomorphisms between this tensor product and the Czech complex tensored, and also to this Koszul complex with respect to the inverse polynomials. And I call the cohomology in this way. Okay, I have here homology and here cohomology. So I have a dual construction. I have in this way an expression as a Czech complex, and in this way an expression as a co-Czech complex. Okay. Now we come to an important problem. What are the homology and cohomology here? And for the first of all, I can have I have an interpretation as Czech in terms of Czech and Koszul complexes, but maybe under some additional assumptions, I get some better information. And to this end, I want to say something about to completions and local cohomology. To this end, let me say an inverse system is called pro-zero if for all n there is an integer m, so that a map in the system becomes zero. And remember that this system with a multiplication by x is pro-zero if and only if this is a zero map here. So for all n, I have an n, so such that this is a zero map. This is just by definition, and this holds if and only if M is of bounded X torsion. Okay. If I have an inverse system which is pro-zero, it comes out that the inverse limit and the first derived functor of the inverse limit vanishes, but the converse is not true. I have the following example here. I take the formal power series ring in one variable over a field, and I define the inverse system in the following way. I define the modules, the ring itself, and the transition map is multiplication by x. This is neither surjective nor pro-zero, but the inverse limit and the first derived functor of the inverse limit vanishes. This is because by the definition of the inverse limit is a kernel of this, and the first derived functor is a co-kernel, but this map is bijective. This is not so difficult to check, and so I have the vanishing of the both of these members. And note that this is not true for the polynomial ring. One has to have work with the formal power series here. Okay, let me come back to the notion of bounded torsion. For if R is of bounded torsion, this is the same as F is of bounded torsion for any flat R module, because the tensor product commutes here. And what I know here, the Czech homology with respect to X for any injective module vanishes. And this means, on the other side, that I modulo the zeros Czech homology is X divisible for any injective module. I will give you a sketch of proof here, because this is a typical proof for some more advanced things coming later. If I take the Czech complex here in the middle, the zero is a kernel and H1 is a co-kernel, and this gives an exact sequence. And This homomorphism set, which is isomorphic, is a direct system, and the limit of this direct system is just H1, as I noted before. And if I have a bounded torsion, this means this map here becomes 0, and I have a 0 map here, and that means this direct limit vanishes. Okay, and for the converse, fix n and make an injection of this guy into an injective module. And because by assumption this is 0, it yields that the multiplication map is 0, because I can make a composition, and this is 0. If this is injective, that means this map is 0. Okay, and what comes out, sorry, what comes out here, if R is of bounded X torsion, it follows by the vanishing for any injective module that this cohomology is just the local cohomology of M with respect to the single element. This is easy to see because by the axiomatic characterization of derived functors, they coincide for I equal to 0, for injective it vanishes, and they respect short exact sequences. Okay, so here let me say something about derived functors, namely the section functor, as we have seen in the last in a talk 2 weeks ago, and the completion is the inverse limit of this guys. And if M is an injective resolution and F is a flat resolution of M, I defined the local cohomology in this way, and the left-derived functors of the completion in this way. Okay, and I have here that the zero's local cohomology is isomorphic to the section functor with respect to A, where A is the ideal I have in mind, and this is a submodule of M. For the completion, this is a little bit more difficult because the completion is not left exact. So I have a map from M to the zero's derived functor and in surjection to the completion. In general, the last one is not isomorphic. Okay, and we can do again extension to complexes. So one needs to, something more about injective resolutions and flat resolutions for complexes, in particular for infinite complexes, as it was done by Spaltenstein in his work. Okay, let me continue with the notion of weakly pro-regular sequences. This has an interesting story, which I will explain in more detail in my second talk next week. For a sequence X and an integer n, I define X up n in brackets, the sequence of the powers for n. And I have here, by the definition of the Koszul complexes, I have a natural map between the Koszul complex for the sequence with the power m to the power n. And it induces a natural map, of course, in homology. And we say that X is m weakly pro-regular if this sequence is pro-zero with respect to the natural maps for all positive I. This looks a little bit artificial. And originally, the notion of pro-regular sequence came into play. But for some things we have here in mind, we need this weaker condition of weakly pro-regular sequences. Okay, so I have that this map in between becomes 0. And I say X is weakly pro-regular if this R weakly pro-regular for the ring. Okay, and an element is weakly pro-regular if and only if M is of bounded X torsion. This is easy to see because the first cohomology for a single element consists just of the annihilator with respect to M. Note this one here. Okay. Okay. I want to say something about a characterization of pro-regular sequences. Namely, I have the following diagram here. I have here the natural map, and this is the natural map of the Koszul complexes, and here's the natural map induced by the surjections. And this diagram becomes commutative, and I have the first characterization of weakly M pro-regular sequences if and only if this cohomology is pro-zero for all positive I. Okay, what is of some interest here, a characterization of weakly M pro-regular. This is pro-zero just for M, and if I tensor with a flat module, this is the same. And this is new. I have the direct limit of the Koszul co-complex with respect to this module becomes 0 for all positive I and I injective. And this is the same as to say that the Czech cohomology vanishes for all positive I and I injective. Okay, let me give another characterization for weakly pro-regulars. That means for the ring itself instead of the module. I have here the vanishing for all pairs of injective module, where I take here the Czech homology, and this is the same as to take an injective co-generator instead of J. Okay, let me come to the end for today. I have the following corollary. I have the vanishing for if X is M weakly pro-regular of this homology, and this means nothing else that this is the right resolution of the section functor, and dually I have here that this is the left resolution of the completion of M with respect to any flat module. Okay, and what I have here is if X is weakly pro-regular and A is an ideal, I have the following expressions. The local cohomology, the I's local cohomology with respect to A is the I's local cohomology of the Czech complex, and this is isomorphic to the I's cohomology of this Koszul complex with respect to the inverse polynomial module. And the same for the completion. I have that the left-derived functors of the completion are isomorphic to the Czech homology, and this is isomorphic to the Koszul homology, I's Koszul homology with respect to the formal power series module. Okay, and in case of a Noetherian ring, so let me stop in a few minutes, any sequence is weakly pro-regular. What is important to show that the Czech homology, the Czech cohomology with respect to X vanishes for all positive I and all injective modules. One makes an induction on K, that means the number of elements of the sequence, and I enlarge the sequence by one element, xk plus 1, and I have the short exact sequence here of the Czech cohomology, and the vanishing is okay for positive I, namely this is 0, and this is 0, and then I have this is 0. Only for I equal to 1 it becomes difficult. Namely, for I equal to 1, I have here the vanishing by inductive hypothesis, but not here. But what do I know in case of an Noetherian ring? This one is just the section functor of an injective module, and it is itself injective. And this completes the proof. Okay, the converse is not true. Take, for example, this ring in infinite, this power series ring in infinite number of variables, and you mod out this idea to this power C, and then you have that all for all Koszul homologies, this map is 0. So that means for any sequence you have the corresponding maps is pro 0, but this is of course not Noetherian. Okay, let me stop here, and I will come back to this example in my next talk. Okay, thank you very much.
Thank you, Mr. Schenzel, for the nice talk. So any question or remark concerning the first presentation, the first talk today, Mr. Schenzel? So if I understand correctly, the main emphasis of this work is for the KM, not necessarily Noetherian.
Yes, that's right.
Yeah.
That's right. Because I will explain it a little bit later. The starting point of this work was a joint work of Joe Lippmann, where he started to introduce this kind of investigations in the non-Noetherian case.
Okay.
I will come back to this next time.
So the ring is if the ring is the Noetherian and the module is not finitely generated, is that this?
You can work even in a Noetherian ring with non-finitely generated modules in this case. But at the present, the new point is that you might give an interpretation of the local cohomology, even in case of a Noetherian ring, as a cohomology of a certain Czech, of a certain Koszul complex. You have a single Koszul complex, and you can describe the Koszul homology as an isomorphic to the local cohomology, respectively the Koszul complex and the left-derived functors of the completion. You can see it here. Let me see. That is a point. Here, even as I mentioned, if the ring is Noetherian or not, if you have a weakly pro-regular sequence, you can give the local cohomology as well as a left-derived functors of the completion an expression here as a Koszul complex with respect to the inverse polynomials, and here with a homology for the formal power series modules. And this is even new in the case of a Noetherian ring. And this works for any ring and any module, and even for complexes, you can extend it to complexes. Okay.
So any comment from other participants?
Sorry?
Any other comment or question?
Yes, Peter, I have a question about completion. So you mentioned completion with respect to one element of a module.
Yes.
But what about completion with respect to an ideal? Can it be realized as homology? Did you mention that?
Yes. Okay, let me come back to this slide. You can see it here. The left-derived functor of the completion is just a Koszul homology. or just a Czech homology, if you like. This works for any ideal, provided it is generated by a weakly pro-regular sequence. And without this assumption, you have just an isomorphism of the Czech cohomology, respectively the Czech homology, to some Koszul homologies. Okay. In my talk next week, I will give a relation to the notion of pro-regular sequences as they were introduced by Greenlees and May, respectively by Lippmann and his co-workers. And I will illustrate you the difference to the weakly pro-regular sequences. So this is some advertisement for next week.
Okay.
Thank you. Thank you very much.
Thank you. It seems that no more questions. Then I invite everybody to come together here next week. Okay. This next week.
Yeah. Thank you.
Thank you.
Okay. I thank you.